The physical reality of a computer, long before any code exists, is just a high-speed stream of electrical pulses. At the hardware level, RAM possesses no concept of integers, text, or structure. It registers only the presence or absence of an electrical charge. Early programming required engineers to manually track these charges, mapping every logical operation to specific physical machine addresses. Without structure, random access memory is an infinite grid of raw hexadecimal addresses that shift and overwrite themselves constantly. This creates a significant hurdle: how to reliably map, store, and manipulate human-readable data within this volatile physical architecture. Hardware remains a series of disconnected signals until a structural abstraction is applied to connect human intent to the silicon. The variable serves as that connection, a specific architectural space physically reserved within the RAM. It functions as a labeled container. By declaring a variable, we map a symbolic name to a precise hardware coordinate. In C++, we claim this memory using a specific declaration, int x equals 10. Executing this command requires the programmer to define three things: the structural size of the container, a label to identify it, and the initial data payload. Mastering C++ begins with understanding how variables interact with hardware and why the compiler requires such strict rules for their declaration. Ultimately, declaring a variable converts this chaotic raw hardware into a perfectly structured environment, totally ready for complex logical operations. To see how this works internally, we can return to our container and plot of land model. First, the compiler surveys the memory. It establishes a physical boundary based on the data type, ensuring the variable occupies the correct amount of space. Next, we attach an identifier, the name x, to that physical address. Finally, the assignment phase drops the actual data into the container. While the physical address and the name stay the same, the data inside can be swapped out during runtime. These labels should be as descriptive as possible, like student name, to provide a clear map for any engineer who reads the code in the future. These names help the programmer navigate the system, but for the compiler, the structural boundary of the data type is the only thing that matters. This system relies on static typing, where the compiler increments the exact memory footprint of every variable before the program ever runs. We can see the impact of this by comparing C++ to a dynamically typed language like Python. Python infers types at runtime. The system uses processing cycles to build and resize the container while the code is already executing. C++ demands that the container be locked in advance. The compiler mathematically locks a rigid, exact byte-sized container before the 10-block approaches. Defining the memory footprint at compile time removes the need for the system to make calculations about container size during execution. This results in faster execution speeds and highly predictable memory management. Of course, this places more responsibility on the programmer to be explicit about every piece of data they use. C++ favors the execution speed of pre-allocated memory over the runtime convenience of dynamic inference. Because the compiler relies on this level of precision, the rules for naming these identifiers are strictly enforced. The compiler's lexer scans the code for any ambiguity. If a name doesn't follow the rules, the translation to machine code fails immediately. For instance, a variable name can include a number, but it cannot begin with a digit. Spaces are also prohibited. The lexer interprets a space as the end of a command, which breaks the logic. Multi-word names must be joined by underscores or formatted in camel case. Special characters like the @ symbol or exclamation point are restricted because they are reserved for mathematical or logical operations. There are also roughly 95 reserved keywords that define the C++ language itself. You cannot name a variable after a keyword, as the compiler would confuse your container for a built-in command. Lexical integrity ensures that the compiler can generate a stable machine translation without hitting a mathematical dead end. One of the most frequent errors in variable declaration involves case sensitivity. To a computer, an uppercase A and a lowercase a are not different versions of the same letter. They are two distinct integer values. Names that look similar to us are completely unique to the system. Declaring these three variations results in three entirely separate containers. A single capitalized letter in the wrong place can cause the program to look for data in a container that hasn't been initialized. In systems programming, a single keystroke changes the physical location where the machine looks for its data.
By mapping thousands of individual variables together, we construct the entire complex state of a running program. This creates a vast network of interconnected memory plots, each with its own specific name and size. Variables are the primary architectural tool for organizing physical machine memory through logical human names. Following these strict typing and lexical rules allows the compiler to turn our code into highly efficient machine instructions. But having a container only solves half the problem. C++ still requires us to know exactly how much space that container needs. We have to ask, how much memory does an integer actually take up compared to a single character? Calculating the precise byte sizing of these primitive types allows us to architect systems that utilize every available bit of physical memory.